Okay. Have you ever been doing something totally normal, like, plugging in your phone or maybe boiling the kettle, and just for a second wondered, what's actually going on inside the walls?
Mm-hmm.
Or maybe you've heard a little hum somewhere, or worse, had a breaker trip and just felt, well, a bit confused.
Happens all the time.
Well, that kind of hidden world of electricity in our homes, that's exactly what we're digging into today. We want to demystify two uh, really fundamental ideas: load and overload.
Yeah. And the mission here is really to take you from just, using electricity to actually understanding it a bit better.
Especially if you want the basics without getting totally lost in technical jargon, right?
Exactly. It's fascinating because these concepts, load and overload, they're operating constantly in our daily lives, often completely under the radar.
Right. Like when?
Well, from the second you flip a light switch or run the washing machine, you're interacting with them. So our goal for this deep dive is to sort of pull back that curtain, give you that foundational knowledge so you don't just operate your stuff, but you actually get a feel for the electrical forces at work.
And maybe, hopefully prevent a household mishap or two along the way.
That's the idea. Think of it as giving you some practical insights, especially now our homes are getting so, connected.
Okay, so let's start right at the beginning. The basic building block,
Mm,
the load. Usually in any system, you've got something that provides and something that uses, right?
right, like a producer and a consumer.
Yeah, like a baker makes bread and we buy it and eat it. Or a factory makes a phone and we use the phone.
Mm.
So talking electricity, there's a source providing the power. But what's on the other end? What's actually using it?
That's exactly the right way to frame it. In the world of electricity, you have the power plants, the utility companies. They're the producers. They generate and supply the electricity. And then pretty much everything that uses that electricity, whether it's in your house, your office, a factory, whatever, that becomes what we call an electrical load.
Okay, so load is the technical term for the user.
Precisely. It's quite simply any device that consumes power within an electrical circuit.
Gotcha. So can you give us some simple everyday examples? Like what are the loads maybe running in my house right now?
Absolutely. Just look around, think about nearly every single device you plug in or switch on.
With the fridge.
Your refrigerator, definitely. Humming away, keeping food cold, that's a load. The lights you have on, loads.
Air conditioner, phone charger.
Yep, air conditioner cooling the room, the charger for your phone, even your TV, they're all consuming electricity. So they are all loads.
So basically anything that takes electricity and turns it into something else.
You've got it. Takes electricity from the source and converts it into another form of energy. Could be light, heat, motion, sound. It's a load.
Okay.
And just to be clear, the load is the opposite of the power source itself, the thing supplying the electricity. Right.
And when you connect that power source to the load, you complete what we call an electrical circuit.
That makes a lot of sense. Power comes from the source, goes through the circuit, gets used by the load. Seems pretty straightforward.
It is at its core.
But I feel like I've heard there can be different kinds of loads. Does that complicate things? For our deep dive today, what's the easiest way to think about them, especially if you're just starting out?
That's a good question because you're right, not all loads act exactly the same way. We talk about resistive, capacitive, and inductive loads. They have different electrical characteristics.
Okay. Maybe let's not go too deep there yet.
No, let's keep it simple.
Mhm.
For understanding the basics, especially around household safety, let's just focus on resistive loads.
Resistive loads, okay.
They're super common in our homes and honestly the easiest concept to grasp. What's interesting here is that resistive loads are devices that primarily convert electrical energy straight into heat.
Ah, okay. So things that are meant to get hot. Exactly right. Think about really obvious things. An electric iron, right? An electric space heater.
Toaster, electric stove.
Perfect examples, the heating elements in those. And older incandescent light bulbs are actually a classic example too.
Really? I mean, they make light, but
They do make light, yes, but a huge chunk of the electrical energy they use is actually just wasted as heat.
that's why they get so hot.
Precisely.
Uh-huh.
And that inefficiency, that heat loss, is a key reason why things like modern LED bulbs are so much better. LEDs are much less resistive in that sense. They convert energy to light far more efficiently without chucking out loads of heat.
That's a great aha moment right there, thinking about efficiency and heat loss with those old bulbs. Okay, so we have our loads drawing power,
Mm-hmm.
but what happens when that demand gets, well, too much? This is where it gets really interesting, I think. I'm imagining, like, trying to stuff 10 suitcases into a tiny car meant for 3.
Good analogy.
You might jam them in, but the car's groaning, the suspension's bottoming out. It's just not working right. It's completely overloaded. How does that apply to electricity?
That analogy paints a very clear picture, and yeah, the strain is quite literal for electrical systems too. This brings us right to our next key term, overload.
Okay.
For electrical devices, for circuits, overload means they are trying to handle more power or maybe do more work than their normal, designed capacity.
It's like pushing them too hard.
Exactly. For instance, say an electrical circuit, the wiring in your wall, is safely designed to carry maybe 10 amps of current.
Right.
But suddenly, maybe you plug in too many things and it's trying to carry 15 amps. That circuit is now experiencing an overload.
Or like a motor example.
Yeah, think of a motor designed to run a pump at a certain steady pressure. If something causes that pressure to shoot up significantly, the motor has to work much harder. It becomes overloaded.
Okay, so it's not just a quick blip. It's a sustained demand that's beyond what it's built for. What's the actual danger here, though? Is it just, the breaker trips, annoyance? Or could an overload cause something really serious at home?
That's a really crucial question because the dangers, they definitely go beyond just inconvenience. An overloaded electrical circuit or an overloaded device, it will overheat. That's almost guaranteed.
Okay, overheating. Sounds bad.
It is. It can lead to immediate malfunction. Maybe the device just stops working. Or, in really bad cases, it could permanently damage the appliance itself.
Right.
But here's something often overlooked. Sometimes the biggest danger isn't a sudden fire. It's the slow, cumulative damage to the insulation around the wires.
How so?
Well, repeated overloads, even small ones, can make that plastic insulation brittle over time. It degrades, it cracks.
Oh, wow.
And that creates a hidden hazard, maybe years down the line, long after you forgot about tripping that breaker. It's a much more serious fire risk then, a sort of silent threat to your home's electrical safety.
That is genuinely unsettling. That idea of a hidden creeping danger building up. So it sounds like engineers definitely thought about safety. What about just us?
Yeah.
Human error. What kind of common mistakes do people make that these safety things have to protect us from? I mean, it's not like a light bulb just explodes the second you go 1 watt over, right? There must be some wiggle room.
You're absolutely right. And yes, engineers definitely factor that in. Most devices, most circuits, they do have a slight overload tolerance. Think of it as a small buffer zone.
A safety margin.
Exactly, a little bit of grace built in. But just relying on that buffer is definitely risky.
So what are the common slip-ups then?
Oh, the classic one is plugging too many high-power things into one single power strip or extension cord.
Like what kind of things?
Think a space heater, maybe a hairdryer, and perhaps a kettle or microwave, all on the same strip, plugged into one wall socket.
Yeah, I can see how that adds up quickly.
It does. Each one draws a lot of current. Combine them on one circuit, and you can easily blow past its design limit. That's why, beyond that little bit of tolerance, we have dedicated safety devices installed. They're there to step in before things get really bad.
Okay, these dedicated devices.
Yeah.
The silent guardians protecting us from ourselves sometimes. What are they?
Generally, we're talking about things like fuses, circuit breakers, and maybe overload relays for bigger equipment.
Yeah.
Their whole job is specifically to detect that overload condition and just automatically cut the power. Shut it down to protect the circuit, protect the equipment.
A diffuse. How does that work?
A fuse is actually pretty clever in its simplicity. It's basically a deliberate weak link. Inside, there's a thin piece of metal wire designed to melt and break the connection if the current gets too high.
So it sacrifices itself.
Exactly. It blows to save the rest of the system from damage. A circuit breaker does a similar job, but it's more like a switch.
The thing's in the main panel box.
Yep. It trips, cuts the power, but you can usually reset it by flipping the switch back after you fix the overload problem, of course. Remove the extra devices.
Okay. So when an overload does happen, where's the first place you might actually see or feel a problem? You mentioned overheating. Often it's the wires themselves, right?
It's very often, yes.
Which feels critical because those wires are hidden away in our walls. Out of sight, out of mind, but doing some heavy lifting.
They certainly are, and they absolutely have limits. Every electrical wire has a maximum safe current it can carry without getting dangerously hot. We call this its allowable current.
Allowable current. Okay.
Now, even when things are working normally, current flowing through a wire always generates some heat. That's just physics, down to its electrical resistance.
A little bit of heat is normal then.
A little bit, yes. But if the current consistently goes above this allowable limit, the wire will get excessively hot, dangerously hot.
And that's where the risk comes in.
That's exactly it. This serious overheating can quickly melt the wire's insulation, that plastic coating. If that melts away, you've got bare, live conductors exposed.
Which could touch, spark, fire.
Worst case scenario, yes, an electrical fire. And that's why preventing excessive current, preventing overload for long periods is just so incredibly important for safety.
So it's not just about protecting the extensive appliance you plugged in, but the actual house wiring itself.
Absolutely. Protecting the infrastructure is paramount.
How do engineers figure out this allowable current? It sounds like it could depend on a lot of things.
It does. And it's a testament to the careful engineering that goes into building codes and safety standards. Allowable current isn't just one magic number for a wire.
Depends on.
It depends on several key factors. The thickness of the wire. Thicker wires can generally carry more current. The material it's made from, usually copper or sometimes aluminum. And crucially, how it's installed.
How it's installed, like in the wall.
Exactly. Think about it. A wire running freely in open air can get rid of heat much more easily than a wire bundled tightly with 10 other wires inside a wall cavity packed with insulation.
Ah, okay, that makes sense. Heat gets trapped.
Precisely. So engineers use detailed tables and standards for this. For example, a specific size of wire, say a 2.5 square millimeter insulated copper wire. If it's installed using a method called A1, which basically means it's inside a conduit, inside an insulated wall, might have an allowable current of maybe 19.5 amps.
Wow, that's specific.
It has to be. That kind of precision, accounting for insulation details, is what ensures your home's electrical system is safe. It really makes you appreciate those, humble wires behind the plasterboard. They're working harder than we think.
It absolutely does. Okay, so let's try and bring this all together. One of the main reasons we get too much current flowing, which I think you called overcurrent.
Yes, overcurrent is the general term.
Right. So a major cause of overcurrent is precisely what we've been discussing, overload.
Correct. Overload is a specific type of overcurrent situation.
The more stuff you pile onto one circuit, the more current it tries to draw, putting more strain on the wires, the devices. It's all linked.
It's all directly connected.
And it really seems like our homes are thankfully packed with these safety measures.
They truly are, which raises the practical question, I suppose. How do we actually prevent these dangerous situations in our homes day to day beyond not plugging in everything at once?
Yeah.
Well, this is where those devices we mentioned, like circuit breakers, really earn their keep. The main electrical panel, sometimes called a fuse box, though usually breakers now.
Yeah, usually near where the power comes into the house. Big gray box.
That's the one. Inside, you've got several circuit breakers lined up. They act as simple on-off switches for different circuits, lights in the kitchen, outlets in the bedroom, etc.
Right, I flipped those before.
But their main job, their critical safety function, is to automatically trip, switch off, and cut the power when they detect an overload or another dangerous fault like a short circuit. That stops the current flow immediately, preventing damage or potential fire.
And those overload relays you mentioned, are they in homes too?
Less common in standard homes. Overload relays are typically used for protecting more powerful equipment, especially things with motors, like in industrial settings or maybe for a very large home air conditioning unit. They sense the motor straining under overload and can trigger specific actions to shut it down safely.
Okay, wow. We have definitely unpacked quite a bit today. From getting our heads around the idea that, your fridge is just an electrical load, to realizing why plugging too much into that one power strip can actually slowly, maybe dangerously, degrade your house wiring over time.
Yeah.
You've hopefully gained some really fundamental practical knowledge about the electricity that powers your whole life.
Thankfully.
So maybe next time you plug something in or just flick a light switch, you'll have a bit more appreciation for all that unseen work happening in the circuits and those incredibly clever safety measures protecting you.
Turning the bzoot of confusion into an aha moment.
Exactly. Making that feeling of information overload turn into some real clarity.
And if we sort of take a step back and think about the future, consider all the new smart home gadgets constantly being added to our home circuits.
Oh yeah, smart speakers, smart lights, connected everything.
Right. This does raise an interesting question, doesn't it? How might understanding load, what each device draws, and overload the limits of your circuits, how might that actually impact your choices when you're building or expanding a smart home?
That's a really good point. It's not just about convenience then.
Not at all. Knowing these principles helps you make sure you're building in not just cool features, but also crucial safety and efficiency into what's becoming an increasingly connected and, let's face it, power-hungry world. Something to think about as technology keeps evolving.